So, welcome to the tutorial session of fluid mechanics and myself Chaitanya. So, the problem that we are going to solve today is this: water at room temperature flows at the same volumetric flow rate Q equals to 9.4 into 10 power minus 4 meter cube per second through two ducts. One is the round pipe, other is the annular pipe, which you can see in the figure, and all walls are made of commercial steel and both ducts are of same length and the dimensions are given. So, our objective is to calculate the head loss in the two pipes and comment on the efficiency of the two pipes. So, let us see how to solve this. So, the geometry is, one is a round one, other is an annular pipe. So, if you look at the dimensions, R is 15 mm, A is 25 mm. So, R is 15 mm, A is 25. So, the first step is to calculate the unknown, which is B. So, the information that is given is the cross sectional area of two ducts is equal. So, therefore, the cross sectional area of round pipe is equal to cross sectional area of the annular pipe. So, this gives us pi r square is equal to pi into a square minus b square. So, we know r, we know a, which is 25 mm and this is 15 mm, and therefore, we can calculate b, which is going to be 20 mm. So, therefore, we know all the dimensions in the problem. Now, we need to calculate the head loss in the circular pipe and the annular pipe. So, let us first calculate the head loss in the circular pipe. So, to do that, first we need to calculate the Reynolds number, and for that we need the velocity. In the problem, the flow rate is given as 9.4 into 10 power minus 4 meter cube per second, and we know the cross sectional area, which is pi r square. From this we can calculate V as Q by A, which gives us 1.33 meter per second. So, with this information we can calculate the Reynolds number, which is V rho by nu So, this is going to be 39,700, and this is, therefore, the flow is turbulent in this problem. Therefore, one needs to use the Moody chart to calculate the friction factor and use that to calculate the head loss. So, for the commercial steel, as they have mentioned, the pipe is made of commercial steel and the epsilon by d value is 0.00153. So, one can use this epsilon by d value and the Reynolds number. Using both of these, one can calculate the frictional coefficient from Moody chart, which is 0.0261, and from this one can calculate the head loss using HF by L is nothing but F by D into V square by 2Z. So, we have the information of F, D, and we know velocity and we know gravitational constant 9.81 meter per second. So, substituting all this, we can get HF by L as 0.0785. So, therefore, for the circular pipe, the head loss is 0.0785. So, it is meter per second square, sorry. So, therefore, we have calculated the head loss in a circular pipe. We will repeat the calculations for the annular pipe, but in the case of an annular pipe, we need to use the hydraulic diameter. So, calculations for annular pipe. So, in the case of an annular pipe, we need to use the hydraulic diameter, which is defined as 4 times of area by wetted perimeter. So, for this geometry, which is annular pipe, this is A and this is what we have B. The area is pi times A square minus B square, and this is going to be pi times A plus B. 2 pi r, and for annulars is 2 pi r A plus B. So, this gives us 2 into A minus B. So, this is the hydraulic diameter, and so therefore, we calculate the Reynolds number based on this hydraulic diameter, which is velocity dH by nu. So, as we have as it is given in the question, the cross sectional areas of both circular and annular pipe are same. Therefore, the fluid velocity in both the pipes will be the same because the volumetric flow rate remains same, and we can calculate the hydraulic diameter and we know the kinematic viscosity. Substituting all this, we will get the Reynolds number as 26,500. Therefore, even in the annular pipe, the flow is turbulent, and here it is going to be 0.023 epsilon by dH value, from which we can calculate F Moody, which is 0.0291. So, now we have the friction factor, from which we will be able to calculate the head loss in the same way as we did for a circular pipe. So, by now it is going to be an approximate value because we are using the hydraulic diameter concept. So, this will be around 0.131. So, if I look at compare the values of head loss for a circular pipe, it is around 0.0785, and whereas for annulars it is going to be around 0.131. Therefore, it is clear that in the case of an annular pipe, the head loss is more, and it makes sense because in the case of an annular pipe, the fluid is in contact with a more wall area, because the fluid is in contact with the inner wall as well as the outer wall. Therefore, there will be high friction. So, we can say efficiency of circular pipe is greater than efficiency of the annular pipe. So, this is question A. Question B. So, in question B, it was asked to assume. In question B, it was asked to assume in an annular duct, the flow in an annular duct is laminar, and suggest the value of A and B that gives a head loss same as that of a circular pipe. So, here what we do is that we have an expression for head loss, and we were asked that the flow, assume that the flow in an annular duct is laminar. Therefore, we can directly calculate F because we have a relation between F and Reynolds number in the case of a laminar flow, and we need to suggest the values of A and B, which is the radius of inner pipe and the outer pipe, that gives the head loss same as that of a circular pipe. So, for the circular pipe, we have obtained the head loss as 0.0785, and in the case of laminar flow, F is 64 by Reynolds number, which is defined based on the hydraulic diameter, and we have one more dH here, and we have V square by 2G. So, if I substitute everything, 64 dH velocity by kinematic viscosity into dH to V square by 2G. So, this V and this V got cancelled off and we end up with an equation. So, if I substitute V as Q by A, because I know volumetric flow rate but not the velocity, and I know area is unknown because we do not know what is A comma B in this problem. Therefore, I will end up with an equation 64 Q by 2G into nu by 4 pi into 1 by A square minus B square into A minus B whole square. So, volumetric flow rate is given in the problem. We know the kinematic viscosity and we know the gravitational constant and everything except A and B. So, I will take the unknowns to one side and I will end up with, if I substitute the corresponding values, I will get. So, this is the equation that governs the values of A and B. And if we assume, if you take the value of A equals to 25, which is given in the schematic, the value of B that we get is around 21 mm. So, one can get, if you want to have the efficiency of an annular pipe same as that of a circular pipe, then we need to have a very thin annular ring. So, you can just see this is like a 21 mm and this is 25 mm. So, this should be the annular parameter that one should use to get the head loss same as that of a circular pipe. So, therefore, this is about this question. Now, let us move on to the second question. So, in this question we use the concept of displacement thickness to calculate the pressure gradient and the mean velocity. So, the question goes like this: air at 20 degrees centigrade and 1 atmosphere enters a 40 centimeter square duct as shown in the figure, and using the displacement thickness concept we are asked to estimate the mean velocity, the mean pressure in the core of the flow at the position x equal to 3 meters, and what is the average gradient in Pascal per meter in this section. So, let us try to answer this question. So, this is question number 2. So, as they have given air at temperature 20 degrees centigrade, the parameters can be obtained from the corresponding tables, where density is going to be 1.2 kg per meter cube and the viscosity is 1.8 into 10 power minus 5 kg per meter second. So, we know the air properties. Now, we were asked to calculate the velocity at the exit. So, if we look at the question, so we are asked to calculate the mean velocity, which means the velocity at the exit. To calculate that we need to impose the continuity equation, we will get to that, but first let us calculate the Reynolds number, which is defined for this problem as rho u x by mu, and we have an inlet velocity and we know density, which is, so density is 1.2, velocity is 2 meter per second, which is given, and the distance is 3 and viscosity is 1.8 into 10 power minus 5. Substituting all this, we will get the Reynolds number as 4 into 10 power 5, which means the flow is laminar as it is a plate problem. Now, using the displacement thickness concept, as we know the Reynolds number and we know the distance, which is x equal to 3 meters, we will be able to calculate the displacement thickness, which is delta star. So, there are two formulas to calculate delta star. One is based on the exact calculation, which is 1.2 1.721 x by Rex power 1 by 2. So, this is based on the exact calculation, and if we assume the profile in the boundary layer is parabolic, then what we get is something very close to that, which is 1.83 x by Rex power 1 by 2. So, the relative error between these two will be 6%, around 6%. So, now we will use the exact equation. Maybe you can try using the equation that we obtained assuming the flow is parabolic. So, we know x, which is 3 meters, and we know Reynolds number. So, that gives us the delta star as 0.0082 meters. So, it is a rounded decimal. So, now we need to impose the continuity equation. Let us look at the geometry again. We have a fluid entering. So, even before that, let us look at what is displacement thickness and how we can use it to understand this, how to impose the continuity equation. So, suppose you have a flat plate and the fluid is entering. So, and we know that there will be a boundary layer development, and displacement thickness is the measure to quantify the amount by which the outermost streamline gets displaced. So, this is what delta. So, the streamline which is just outside the boundary layer is getting displaced because of the boundary layer effects. So, this displacement is quantified by displacement thickness. So, if you want to impose the continuity equation, so if one wants to impose the continuity equation, so this is fluid which is entering, or the mass flux rho u into A. Now, here the area is changed. So, here the area is based on this height, whereas here area is based on, let us say this is h. So, this is delta star. So, we need to say that rho u h is equal to rho u h plus delta star. So, if we assume it is a square duct, it is like h square into h plus delta square. So, this is the case for a flat plate. Now, if we use the same concept for the given geometry, which is a channel, what we will end up with is, and they have given the dimensions of the channel. This is a 2D channel and they have given it around 40 centimeters. So, here what we get is V into L naught square equals to V exit, which is an unknown, into L naught minus 2 delta star whole square. So, you can see, so this is the inlet velocity. We know inlet velocity, we know the dimensions of the channel, therefore, we can calculate the inlet mass flux, which is rho u into S. And similarly, we know the displacement thickness, and using that we can write the out mass, this is the mass flux out and this is the mass flux in. So, we know the entrance velocity, which is 2 meter per second. L naught is given in the problem, which is 40 centimeters. So, V exit is an unknown, L naught, and we have calculated delta star. So, from this we can calculate V exit as 2.175 meter per second. So, therefore, we have calculated the A part, which is the mean velocity, and then we were asked to calculate the mean pressure in the core of the flow at the position x equal to 3 meters. So, to calculate the pressure, because we have a velocity data and we have an inlet pressure, so we can impose the Bernoulli equation. So, which is P exit plus rho V square by 2 rho V exit square equals to P inlet, or I will define as P0 plus rho by 2 V0 square. So, as the inlet pressure is atmospheric pressure, let us work with the gauge pressure, which means we are subtracting the atmospheric pressure from the given pressures. Therefore, as inlet pressure is already 1 atmosphere, this goes to 0 because we are looking at the gauge pressure. So, what we can get is the P exit, which is rho by 2 times V inlet square minus V exit square. So, this will be around 0.44 pascals. And you should remember that this V exit corresponds to x equals to 3 meters. Therefore, this P exit corresponds to x equal to 3 meters. So, therefore, we have calculated the pressure, and the next question is what is the average pressure gradient in Pascal per meter. So, the pressure gradient is nothing but delta P by x. As we are working with the gauge pressures, we can write delta P as 0.44 and x in the problem is 3, which gives us around 1.5 Pascal per meter. So, therefore, using the displacement thickness concept, we have calculated the mean velocity, and using that mean velocity and the Bernoulli's expression, we have calculated the pressure, and from that we have calculated the pressure gradient. So, in this way we can use the displacement thickness concept in the case of a channel and calculated the exit velocity and the pressure gradient. So, this ends the tutorial. Thank you.